Hello folks, in this video we'll be looking at adding vectors. This video is brought to you by the letter C, which is for coffee, and that's good enough for me. Adding vectors is a little different from adding numbers, and when I say numbers, what I mean is scalars. Scalars are quantities that don't have a direction associated with them, and vectors do have a direction. So velocity is a vector, 25 miles per hour to the north, that's a vector. If it's just say mass, 65 kilograms, not a vector. Now sometimes adding vectors can be very similar to adding scalars. In fact, that's going to be when the vectors are all in the same direction. For example, if we walked 3 meters to the right, and then another 2 meters to the right, then we would end up 5 meters from our starting point. But what if that 3 meter and 2 meter weren't both vectors to the right? What if instead we walk 3 meters right and then 2 meters in this downward direction? In that case, how far do we end from our starting point? Well, it isn't quite as simple as just adding the two numbers together anymore, but we can see that in this case, we have a right triangle, and so we can use Pythagorean Theorem to figure out how far we are from our starting point. So, with Pythagorean Theorem, we say that a squared plus b squared equals c squared. In this case, I'm going to write it as 3 meters squared plus 2 meters squared equals our unknown value, the hypotenuse, that quantity squared, which gives us a value of 3.6 meters equals c. Now, the other piece that we would want to do with this, maybe, is figure out what direction we are from our starting point. We know we're 3.6 meters away from the starting point, but which way? So I'd be interested then in figuring out what this angle theta is. So to figure out that angle theta, I'm going to use some trig. In this case, I know all three sides. I was given the opposite side and the adjacent side, so I'll use those ones just in case I made a mistake in calculating that 3.6. It won't transfer to an error in my angle. So the trig function that deals with opposite and adjacent is tangent. So I'll write that out as tangent of theta equals 2 meters over 3 meters, or theta is equal to the inverse tangent of 2 meters over 3 meters, which gives me an angle theta of 33.7 degrees. That isn't too bad when we're dealing with a right triangle and only two vectors to add. But what if we have a more complicated situation? What if instead I want to figure out how far I am from my starting point after three vectors that look like this? So far we've just done two vectors, and those vectors have either been parallel to each other or perpendicular, so they formed a right triangle. Here we don't have a triangle at all. Our overall vector, our resultant vector, is the name of this. That's the answer when we add vectors. It's going to look something like this. I'll label that R. But how long is that, and in which direction does it act? How would I figure that out when I don't have a right triangle to do trig with? Well, it turns out I'm going to break this down into a series of right triangles. So I'm going to first figure out how far for vector A, how far does vector A take me in the up-down direction? And how far does it take me in the left-right direction? And look at that, that's a right triangle. I'll call this AX and this AY. And I can use trig to figure those things out, assuming that I was given some information about one of those angles. I can do the same thing for vector B and for vector C. At this point I know how far in the x direction, horizontally, and in the y direction, vertically, each one of these vectors has taken us. Those x and y pieces of these vectors we call the components of the vectors, and that process is known as vector resolution. Well, what does that get me? What it gets me is how far overall in the x direction and overall in the y direction this overall vector has to go. In the x direction, I'll have to go ax plus bx plus cx. In the y direction, I'll have to go ay plus by plus cy. I'll have numbers for each of those. So now I have this new right triangle where r is the hypotenuse. One leg is ax plus bx plus cx. The other leg is ay plus by plus cy. With that information, then, I can use the Pythagorean Theorem to figure out the length of r, and I can use inverse tangent again to figure out the direction of r. Let's take a look now at an example problem with using this technique. In this problem, we have a car that begins by driving 55 miles to the west. I'll call that vector A. Then the next path we'll call vector B. It travels 25 miles at 10 degrees west of north, and then finishes out the trip with another 30 miles at 30 degrees east of north. We're asked then to figure out overall how far and in which direction is the car from its starting point. That's what displacement, resultant displacement, means. So in this diagram we want r and theta. So we're going to start out the same way we did with the general problem. In fact, all these problems are really worked exactly the same way, which makes them pretty easy once you know how to do it, because they're all going to look the same. But we'll find the x and y pieces for each of the vectors shown. Sometimes on a diagram like this it gets a little cramped, so I like to redraw these vectors all on their own for finding their components. Let's start with vector A. Vector A is straight to the west, so that's going to make this pretty easy to find the x and y pieces. In the x direction, it's 55 miles. Since that's pointing to the left on my paper, I'm going to make that a negative, and anything that points to the right on my paper, I'll make a positive, just so I don't forget that, oh yeah, those are in opposite directions. The y part of that, well, it's not going up or down at all, so that's going to be just 0. On to vector B now. Vector B does have both an x and a y element to it. Vector B is pointing up and to the left, so the y part is going up, the x part is going to the left. Those form a right triangle when I draw them with the original vector B, so I can use some trig to solve for those. Since bx is on the opposite side of that triangle from the 10 degrees, I would use sine of 10 degrees equals bx over that 25 miles to find bx. And in this case, I get 4.34 meters, or miles rather. And since that's pointing to the left, I'll go ahead and put that negative sign in. Cosine is used to find y because it's the adjacent side on this triangle, adjacent to the 10-degree angle anyway. And that's going to give us 24.6 miles. And now for vector C. Vector C points up and to the right, so I'm dividing this up into how far up and how far to the right that vector takes us. To get Cx, again, I'll use sine of 30 degrees equals Cx over 30. To get Cy, I'll use cosine of 30 degrees equals Cy over 30 miles. And then I'll get, for my answers, 15 miles for the x direction and 25.98 miles for the y direction. The y is pointing upwards, so that'll be a positive. The x is pointing to the right, so that's a positive as well. Next step, I need to figure out overall how far do we go in the x direction, and overall how far do we go in the y direction, and then I can go about solving for that r vector. Overall in the x direction, we go negative 55 miles plus negative 4.34 miles plus a positive 15 miles. That's going to give us an x component for our resultant displacement of negative 44.34 miles. In the y direction, the overall displacement will be ay plus by plus cy. Here that's going to be 0 plus 24.6 plus 25.98. Those are both positives. So we're going to get overall in the y direction 50.58 miles. Now I can construct a new triangle which has side lengths of 44.34 miles to the left because it's negative, and then 50.58 miles upward, or I could change the order of that, doesn't matter which way we set that up, and we can solve for our overall resultant displacement. At this point, the problem looks just like the first one we did, where we had vectors at perpendicular directions to each other, and we'll solve it the same way. To get the length of the hypotenuse, that's our overall displacement's magnitude, we'll do Pythagorean Theorem. A squared plus b squared equals c squared. In this case, that'll be 50.58 miles squared plus 44.34 miles squared equals r squared, the magnitude of the resultant displacement squared. And when we do the calculations, we find then that r gets a value of 67.3 miles. We also need to get the direction. We're looking for displacement that has both a magnitude and a direction with it. That's a vector quantity. So in this case, we'll use again the inverse tangent function to find theta, where theta is equal to the inverse tangent of the opposite side, 50.58 miles, over the adjacent side, 44.34 miles, which gives us a value theta equal 48.8 degrees. And the last step in these problems is to write out our answer so that it's one coherent statement. So on this one, I would write out that the car's resultant displacement is 67.3 miles at 48.8 degrees, and then that north of west part, well, if it had been straight in this direction, that would have been west. I know that it's 48.8 degrees away from west, and it's rotating up this way, not down this way. Up this way is getting closer to north. So that's 48.8 degrees here. That's north of west. Just to review the process, we started out by drawing the three vectors we were asked to add together. We had these three were our initial vectors, and I drew in the resultant vector as well. The next step after that was to find the x and y components for each one of those given vectors. We added all the x's together to get the overall x vector. We added all the y's together to get the overall y vector. Then we made a new triangle where we had a side length of the overall x distance, the overall y distance. We did Pythagorean Theorem to solve for the magnitude of that hypotenuse, the magnitude of the displacement. We did inverse tangent to find the angle, and then we put it together in one coherent statement. That'll be the same process we use every time we want to add vectors together. We've used displacements, distances for this case, but it works exactly the same way with either velocities or accelerations or forces or momentums or any other vector quantity. We can add those vectors together in exactly the same way. That's all for this video. Thanks for watching, folks. Please be sure to like this video if you learned something from it. Ask a question in the comments section, and if you want to see future videos from me, go ahead and subscribe to this channel. Thanks again.